Hello everyone and welcome. This video will cover C++ debugging techniques. We'll explore methods for finding and fixing bugs in C++ programs, providing you with essential skills to tackle coding challenges effectively. Let's start with the fundamentals. Debugging is the process of identifying and correcting errors in your code. It is a crucial skill for every C++ developer. Effective debugging involves a systematic approach to problem solving. Debugging can take a significant amount of development time, up to 50% in some cases. Here's an example of common C++ bug types. In the main function we have two integers, x which is assigned a value of 5, and y which is assigned a value of 0. There is a logic error to calculate the sum of x and y, but the code subtracts them. Also, there is a potential runtime error where the code attempts to divide x by y, which would lead to a division by 0 error. Now let's discuss the common types of C++ bugs you might encounter. First, there are compile time errors, which include syntax errors such as missing semicolons, incorrect brackets, or typos. Then there are type errors, which involve incompatible data types used in operations. Linker errors occur due to missing function implementations or libraries. And finally, declaration errors, which involve undeclared variables or functions. Next up are the runtime errors, which include memory issues like null pointer dereferences or memory leaks. Logic errors arise from incorrect algorithms or conditions. Arithmetic errors can occur, such as division by 0 or overflows. Resource errors can happen when a file is not found or a network times out. And race conditions can emerge from concurrent access issues in multi-threaded code. Let's explore print debugging. Print debugging is one of the simplest and most straightforward debugging techniques. It involves adding output statements at key points in your code to track variable values and the flow of execution. It doesn't require any special tools, and it can be applied in virtually any coding environment. Here's an example. The calculateSum function takes two integer inputs, a and b. Before calculating the sum, the function prints the input values using standard output. After calculating the sum, it prints the result before returning it. Let's take a look at assertions. Assertions are used to verify assumptions during development. They automatically detect invalid conditions. If an assertion fails, the program terminates, which can be very helpful during development. Assertions are disabled in release builds by default, which means they have no impact on the final product. Here is an example. The function getElementAt takes a vector of integers and an index as input. It uses an assertion to confirm that the index is within the bounds of the vector. If the index is out of bounds, the assertion fails and the program terminates. In the main function, an attempt to access an element at index 5 in a vector of size 3 will trigger the assertion failure. Let's explore the use of debuggers. Debuggers offer a range of features, including breakpoints, which pause the execution of your program at specific lines. They allow you to step through your code line by line to observe its behavior. You can also watch variables to monitor their values as they change. Debuggers provide a call stack, which shows the function call hierarchy, and they support conditional breakpoints that only trigger when certain conditions are met. Some debuggers even allow you to inspect memory contents directly. Here are some popular C++ debuggers. There is the GNU debugger, also known as GDB, which is commonly used through the command line. Then there is the LLVM debugger or LLDB, which is designed for use with the Clang compiler. Visual Studio includes an integrated debugger. CLion, a JetBrains IDE, also has its own debugger. Finally, VS Code can be used with a C++ extension to enable debugging. Let's discuss memory debugging tools. Memory debugging tools are essential for detecting memory errors such as memory leaks, buffer overflows, use after free errors, double free errors, and uninitialized memory access. Some of the popular tools for this purpose are Valgrind, Address Sanitizer, also known as ASIN, and Dr. Memory. Here's an example. It's important to compile the code with address sanitizer to effectively detect memory issues. This code demonstrates a memory leak where memory is allocated but not freed, a buffer overflow where data is written beyond the allocated buffer, and a use after free error where freed memory is accessed. Let's explore logging techniques. Structured logging is more sophisticated than using print statements. It involves assigning different severity levels to log messages, such as info, warning, and error. Logging also includes timestamps and context information. Logging can be enabled or disabled at runtime. Output can be directed to files, the console, or over a network. Here's an example using spdlog, a popular C++ logging library. The divide function logs its entry with the values of the parameters and checks if the divisor b is 0. If it is, it logs an error and throws an exception. Otherwise, it calculates the result, logs it, and returns it. Now, let's examine some effective debugging strategies. A systematic approach involves reproducing the bug to create a reliable test case. Isolating the problem involves narrowing down the section of code that contains the bug. Binary search debugging involves commenting out half the code at a time to quickly identify the problematic area. Rubber duck debugging involves explaining the code to someone or something to clarify your understanding and potentially spot the bug. The divide and conquer strategy involves breaking down complex problems into smaller, more manageable parts. There are also advanced techniques you can try, such as unit testing to identify bugs before they reach production. Static analysis tools like ClangTidy and CPP Check can automatically detect potential issues in your code. Code reviews, where fresh eyes examine your code, can spot issues you might miss. Continuous integration helps catch regressions early in the development process. Defensive programming involves anticipating potential issues and writing code to handle them gracefully. And fuzzing involves automated testing with random inputs to uncover edge cases and vulnerabilities. In conclusion, here is a summary of effective C++ debugging. Debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. Here are some key points to keep in mind. Use a combination of debugging techniques for different scenarios. Master your debugging tools and environment. Develop a systematic debugging mindset. And document bugs and their solutions for future reference. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.